Today we'll talk about repeated measures ANOVA. And there isn't an assignment. There's no homework on repeated measures ANOVA. That's the good news. There is some coverage of it on the exam, however. That's the bad news. So you do have to do the readings and go over the lecture slides again after today. It's not very deep coverage of repeated measures ANOVA, just the top level ideas. And the questions are drawn from the lecture. The readings will help. I'm not saying don't do the readings, but the questions are drawn from the lecture today. But before we start on that, are there any questions I can answer? First, about the material so far, or the exam? Yeah, in the back. One cheat sheet for the final. There was an earlier version of the course outline that said 2. That was a mistake. It was supposed to mean 2 sides of one sheet. So just like the midterm, one page, you can use both sides though. That's been corrected in the course outline. Yeah.
Is there any lab this week?
Is there a lab this week? No. If you had the lab that was leading up to homework 10 already, then there's no lab this week. Then you're done the labs. The TAs may be holding the labs, nevertheless, as a kind of question-answer session if you want. You should confirm with your TA, but there's no need to go if there's no homework. Yeah. All right, let's start in on this. There we go. Okay, repeated measures ANOVA. Final exam. There are a couple of sample questions posted on the course website. It's just going to be like the midterm, just slightly longer and covering more material. So if I were you, or if I were to give you advice about how to study for it, I would start with the lecture slides, because the lecture slides gives you the most important high-level points on each topic. Review the lecture slides, make sure you understand the main concepts. Review your readings that you've done, and review the homeworks. Not the homeworks with an eye towards the code. The code's not going to be tested on the exam. There's going to be 1 or 2 code-ish questions like on the midterm, but really it's not about the code. So review the homeworks not for the code, but for the concepts, the steps in analyzing data using each technique, the concepts that are important to you. You don't need to focus on the teeny tiny details of each thing, focus on the main concepts. And if you've been to class every week and you've kept up, then also trust yourself that it's in your brain. It's in your brain already. Studying is going to consolidate that. And when you get to the final, take a deep breath and trust that it's in there. You just have to let it out. Okay, repeated measures designs. These are sometimes called within subjects or within participant designs. And the idea here is that in contrast to a between subjects design, which we've seen so far, where a participant contributes a score only in one condition, like a participant gets the placebo drug and not the actual drug. In a repeated measures design, a participant contributes a score in every level of that factor. So more than one score. If you only have 2 conditions, placebo versus drug, then you might as well just use paired samples t-test. The repeated measures ANOVA is equivalent to that. So, like between subjects ANOVAs, repeated measures ANOVAs are really useful when you have more than 2 levels of some factor that you're varying. And now each participant gets exposed to every level of that factor. And we'll talk about the pros and cons of that later. So, for example, you might get the same participants measured on their mood either before and then also after some treatment, and then maybe a third time after a week. You might have a study where you're looking at the effects of either placebo versus treatment A versus treatment B on blood pressure. And you can study that in the same participants. where each participant can serve as their own control now. So that's the big advantage, as we'll see, of a repeated measures design, is essentially, one way of putting it is each participant serves as their own control. So whatever the effect is that you're manipulating, like the drug or the dose of the drug, you can compare that within the same participant to the other doses or to the placebo. And that gives you a more powerful test, as we'll see later. Another common repeated measures factor that people look at is time, the behavior or the measure of some thing over several measurement times, over several minutes, or several days, or whatever it is. So time is a very common repeated measures factor. So sometimes you can have participants serve as their own control if there's a control condition, and so you don't need a separate control group. And as we'll see when we look at the numbers, the great advantage is that the variance between levels of a factor ends up being reduced, because you're no longer including the effects of the factor plus inter-subject variability in that estimate, because the inter-subject variability is taken away, because it's the same subject, the same participants. So the variability across levels of the factor, between level 1 and level 2, level 3, placebo, drug 1, drug 2. Those differences are only due to that factor. They're no longer due to differences between individuals, because it's the same individual. So you get more information from each participant in a repeated measures design because they contribute a score in every level of the factor. So if you've got a factor with A levels, then each participant contributes A scores. Whereas in a between subject design, each person only contributes one score. So what that means is that the number of participants that you require to reach a given level of statistical power is often much lower in a within subject design than in a between subject design. So you don't have to recruit as many participants, or you don't have to buy as many mice in a mice breeder if each mouse contributes more than one score. So that's one advantage, is you often need fewer participants in your study. So I said something earlier, we're going to dig into it a bit more. In a repeated measures design, the variability due to individual differences between subjects ends up being removed. Or another way of putting it is it ends up being accounted for. You can calculate that. And you can remove it from the unexplained variance, which is the error term of the ANOVA. And what that means is that the F ratio ends up being bigger, and you get more statistical power. So just like in an ANCOVA, where including a covariate, let you take a chunk out of that error term because you can attribute it to the covariate. Same concept here. It's not a covariate anymore, but it's inter-subject differences. You can account for those now, and you can take that out of the error term. So let's look at an example. And as before in these slides, if you click on that little arrow, you can see the code that's generated each panel, and you can copy and paste that and run it in your own RStudio if you want to follow along. So here's just a made-up data set with 10 subjects, 10 participants. Each participant contributes a score in 4 levels of some factor called factor A. And factor A has 4 levels: A1, A2, A3, A4. So subject 1 contributes a score in each level, subject 2 in each level, and so on. So it's a repeated measures design because it's the same participant in each level of the factor. But just as an exercise, just to show you the development of this, let's pretend for a minute that this is a between subjects design. Okay? So let's just treat this as if it was a between subjects design. We can run an ANOVA, just a regular one-way ANOVA, on that data set, just using the ALB command, and we would get this ANOVA output. We would get the effect of factor A, 3 degrees of freedom. That's the sum of squares due to the variability across levels of A. And 36 residual degrees of freedom, that's the error term. 77 is the sum of squares residuals. That's the sum of squares that's not accounted for by the factor. It's the leftover sum of squares. The residual mean square is the sum of squares divided by degrees of freedom, so that's 77 divided by 36, which is 2.139. That's the denominator of the F ratio, 2.139. The numerator is the mean squared due to the factor, which is 38.9 divided by 3, which is 12.967. So 12.9 over 2.1 is 6.1, and the p-value is 0.0089. It's significant. Good. We've got a significant effect of factor A across the levels, even if we treat this as a between-subjects design. And we ignore the fact that the same participants contribute a score in each level. So this isn't wrong, necessarily. It's just not as good as we can do. What we're missing out on is the fact that some of that total variability is due to differences between participants. So, this participant number 1, their scores are 8, 10, 7, and 5. Let's pretend A1 is some kind of control level, maybe a placebo. Subject 1 starts off at 8. Subject 6 only starts off at 5. That's a big difference, 8 versus 5. That difference between subject 1 in A1 and subject 6 in A1, 8 versus 5, is a difference of 3. That's almost as big as the difference between A1 and A3, right? So different participants are starting off at vastly different starting points. And that variability across those, that variability going up and down, that's included in these estimates of variability. In particular, it's residual. That's leftover variability that's not accounted for by the variability going this way, A1 through A4. So we could try to account for that variability going up and down, the differences between subjects. And we can do that because each subject has a score in all 4 levels of the factor. So let's just pretend, since we have it labeled as subject, let's pretend we're going to do now a kind of a 2-factor between subjects ANOVA. We'll still call it between subjects, even though it's not. And we're going to include in our model not just factor A, but we're going to add a plus subject, since subject is labeled here. Now, we're not doing times subject, right? In a true factorial design with 2 factors, you have factor A, factor B, and then the interaction with factor A by factor B. Here we're just using a plus, which means we want the main effect of factor A, just the main effect of subject, and we're leaving out the interaction between factor A and subject. Okay, so we're just including now the main effect of subject. And so what we get as an ANOVA output now is kind of interesting. Let's have a look. The factor A line, the output, looks the same as it does here, where we don't include subjects. Degrees of freedom is 3, sum of squares is 38.9, mean squares 12.967, but the F value is different. But the degrees of freedom, sum of squares, and mean squares is the same, right? That's just the variance accounted for by A1 versus A2 versus A3 versus A4, ignoring the fact that there are different participants. That's that first line. But now have a look at the residuals. Let's look at that next. We have fewer degrees of freedom for one thing. Now we have 27. And that's because 9 of them are being taken away by the subject main effect. The sum of squared residuals is now 28.6, which is much smaller than it used to be, which was 77, right? 77 used to be all of the sum of squares that are left over once we've accounted for the sum of squares due to the factor, right? That's the leftover, unaccounted for sum of squares, 77. Now we've taken a bite out of that 77. We've removed 48.4 from that 77. The sum of squares that are due to differences across subject is 48.4, and that's being taken out of 77. And indeed, if you add 48.4 to 28.6, you get 77. So that's been taken out of the error term. And now our error term, our mean square, the denominator of the F ratio, is 28.6 divided by 27, which is 1.059. That's much smaller than it used to be, which was 2.139. It's half. It's almost half. So that's why our F value up here is so much bigger. The sum of squares and the mean squares are the same as it used to be over here. But the F value is twice as big, 12 versus 6. And that's because F is equal to mean square, factor A, divided by mean square residuals. And because the mean square residuals is smaller, that's the denominator of the F ratio for the test of the factor. The denominator is smaller, so F becomes bigger. Nothing's changed about factor A, right? We're still accounting for 38.9 sums of squares. That's still the effect of the factor A1 versus A1 versus A2 versus A3 versus A4. It hasn't changed. And the mean square hasn't changed. The only thing that's changed is the thing that we're dividing it by, which is the error term. So just like in ANCOVA, where we've accounted for some of the error term using a covariate, now we've accounted for some of that error term using the main effect of subjects. And the main effect of subjects is just another way of saying inter-subject differences. Differences in the data going this way, up and down. So, because the error term is so much smaller, F is bigger. And of course, the p-value for a bigger F is itself smaller. We get a smaller p-value. So what that means practically is we get a more statistically powerful test of factor A. By accounting for the differences across subject, by including that main effect of subject, and taking a bite out of the error term, explaining some of the variability because it's due to inter-subject differences, we get a more powerful test of the factor A. Even though we haven't changed anything about factor A, we get a more sensitive test about factor A. Now here it doesn't much matter because the p-value is already very small, but it very well could be a situation where if you don't account for the subject factor, the p-value is not significant, and then when you do, it becomes significant. So before I flip to the next slide, are there any questions about that concept so far? We'll repeat some of this, so the details aren't quite solidified yet. Don't worry.
Are you able to do a half-square repeated measure?
Yeah, that's a great question. The question was, I'll rephrase your question. The question was, here we included the main effect of subject. And that's because we used a plus here in the formula. And the question was essentially, could we actually do a fully factorial design here and include the main effect of factor A, the main effect of subject, and the subject by factor interaction? So I'm going to throw that question back to the room. Could we include the interaction term here, factor A by subject? Have a look at the numbers for a second, and I'll get a vote. I mean, in theory and principle, we could. In practice, can we focus on the degrees of freedom column? How many degrees of freedom would be listed for a factor A by subject interaction effect? Do you remember how the degrees of freedom work? So the main effect degrees of freedom is the number of levels minus 1. So 4 minus 1 is 3. The main effect of subject is 10 minus 1, which is 9. The degrees of freedom for the interaction would be what? You don't remember? It's burned into my memory because as an undergrad I had to do all this by hand exams. I see some fingers. What would it be for the interaction effect? No, you don't subtract them. Remember what is it? Well, I'll give you a hint. What would be the symbol for interaction effect? So what would it be?
27.
It would be 27. It would be 4 minus 1 times 10 minus 1, which would be 3 times 9, which is 27. So we take 27 degrees of freedom out of the error term, and oops, we only have 27 degrees of freedom left. If we took all 27 degrees of freedom out of the error term and attributed it to factor A by subject, then we would have to compute the mean square by dividing the sum square by 0. And can you divide by 0? Well, you can do it, but you get infinity. And then our studio would complain to you. Right? So the short answer is we can't, because we don't have enough degrees of freedom left. Yeah.
But what if you're not using the subject as your second factor? Like, what if we have, you're testing two, like, let's say factor A and factor B
Okay.
across different, like, across time. So you have your subject.
Yeah, so now you're talking about a second factor, a second repeated measures factor?
No, a second, just regular factor. Like, if we have two main effects,
Okay.
and then we test those two main effects across time.
So, yeah, so it's essentially what you're, if you test two main effects across time, so A1, A2, A3, A4, and B1, B2, B3, B4, that kind of idea. And then the question is, can you have an A by B interaction?
Or like, I don't know if it, like, for example, in this design, so
Yeah.
we have the levels A1, A2, A3, A4,
Yeah.
and that's just the time, that's the repeated measure.
That's right.
So then, let's say the factors that we're testing for are, so we have male, female, that could be one factor, and another factor could be happy-sad, for example.
Sure. Yeah,
Let's
so
say-
if we have male, female, that would be factor B. And we have one of these tables for male, and another one of those tables for female. And then we would have a main effect of A, because A appears in both of those. And then we have a main effect of B, because we get average across A. And then we could have an A by B interaction.
So you have to do them separately, and then combine.
That's right, yeah. Yeah, so in that case, factor A would be a repeated measures factor, because each participant is measured in each level of that. And then factor B, if it's male-female, would be a between subjects factor, because each participant is only in one category. That's certainly a possible design. We're not going to talk about those kinds of designs in this course, because we ran out of time. But that, as we'll see at the end, that's called a mixed design, where you have one or more factors between and one or more factors within. Yeah, so and a common repeated, a common mixed design where one factor is time and the other factor is some between subjects and duration. Like placebo versus drug versus another drug, and you're measuring concentrations of something in the blood over time. Yeah, so you do that. But in this design, with just one repeated measures factor, as we just saw, the answer is no. You couldn't have a factor by subject interaction because there's no more degrees of freedom left. Now that's kind of a mathematical explanation, but what does that mean? I mean, what does that relate to conceptually, that there aren't any degrees of freedom left? Yeah.
Well, that we're analyzing each participant individually, so we can
Yeah, what you said was we're analyzing each participant individually, so we can no longer find group effects. And I let you phrase that slightly by saying the following. When we're looking at the effect of factor A, we're looking at A1 versus A2 versus A3 versus A4. And we're kind of including everyone in A1 in the A1 estimate, right? And we're computing the mean, and another mean, and another mean, and another mean. And the variance across those data points within each category is our estimate of the within group variability, right? And if we're looking at the main effect of subject, we're kind of combining those four, and then those four, and then those four, and comparing those means across left and right is our estimate of the variability within each group. If we were to try to estimate the A by subject interaction here, then we'd be comparing every individual data point to every other individual data point, which is okay. We can compute that sum of squares. But what would be our estimate of the within group variability? Now we have groups of one. That's kind of what you're saying, right? We have a group of just one data point. And so we can compute a mean. The mean of a number is just a number. But we can no longer compute a measure of variance within that group, or within cell variability. And it's that within cell variability that relates to this error term. That's what this mean square is supposed to estimate. And so if our variability is supposed to be estimated based on one number, the variability is going to be 0, right? There is no variance. It's just one number. So that's why this would end up being 0. So we can't include it. We started off by saying, let's just treat it as a one-way design. We can get this far. And then we sort of realized, no, we can account for another source of variance. It's the intersubject differences. So let's throw that in. And we kind of get carried away. We keep going to an interaction now and take another bite out of the variance. The error term? No, we can't. We can't do the interaction term because we don't have enough data. Okay, so that was pretending it's a one-way design and adding in the effect of subject. And this is just a summary of what happened. Here's just a one-way design with factor A by itself. Here's what happens when you include the subject name. You essentially take this error term, this residuals, and you split it into two. Right? You split off the part of that you can account for by intersubject differences, and that's 48.4 sums of squares. And then the leftover, 77 minus 48.4 is 28.6. That's the new unaccounted for variability. That's the new error term. And that's why these mean square terms change as well. 77 divided by 36 is 2, but 28 divided by 27 is only 1. So you get a smaller mean square. And that's why the F statistic changes for the factor, for the test of the factor. Remember, the sum of squares doesn't change, and the mean squares doesn't change for the factor. It's only the F that changes, and that's because the denominator is now smaller. So you get a bigger F. So for the same sum of squares, for the same mean squares, you get a bigger F and a smaller p-value. So you get a more sensitive test. You don't need as high a sum of squares to get the same F and to get as low a p-value. So a smaller difference across those levels will still be identifiable as a significant effect. So you're more likely to detect the true difference when it's there. So that's kind of the mathematical idea of accounting for those intersubject differences. And so our little kind of what-if experiment where we include the main effective subject as a factor, that actually it ends up being exactly what a repeated measures ANOVA does. It just presents you with that information in a slightly different format. So in R, to do repeated measures ANOVA, you have to use this weird-looking syntax. Instead of just saying plus subject, you say plus capital E error, bracket subject slash factor A. And it is kind of complicated in its uses, but it's a way of telling R that factor A is a repeated measures factor. That the column labeled subject in your data frame is within factor A. That's a weird way of telling R. It's the same subject in each level of factor A. And so what R then shows you is this, which if you compare them, it's the same information as here. At the bottom, you have the test of factor A and its F value and its P value and the residuals. Those are the same numbers as here. It just moves this subject term up into a separate area called error subject. So it literally like separates, doesn't only separate it from the residual, it literally separates it from the output. And that's because conceptually we're not actually interested in testing intersubject differences. We're not really looking for an F statistic or a p-value for the subject differences. All we're really interested in doing is splitting it off from the error term. The thing we're interested in testing is the effect of factor A. There might be intersubject differences, but we're not really interested in testing that. We just want to explain them and get them out of the error term. And so that's what the repeated measures limit does. Questions? Yeah.
So with that error subject section, is there any information there that we would use in our analysis or inferences?
Yeah, so the question was, in this section up here, is there any information in there that we would actually use or report in our analyses? And the answer is no, not usually. When you're reporting the results of the repeated measures ANOVA, you don't typically report any of these numbers in particular. They're not really interpreted. It's this at the bottom that you're interested in. You're interested in the test of the factor. It's kind of like that analysis of covariance, where you include a covariate, and you're not really interested in testing the covariate per se, right? You're interested in testing the factor, now that you've explained some of the variability using the covariate. So really you only report this bottom part. Yeah?
Sorry, you were saying that the way that we use that syntax, we're telling part that it's within, was it factor A or within subject?
Subjects within factor A. Yeah. The bottom line is it's the way that you inform R that factor A is a repeated measures factor. Yeah. I mean, if you were to do it this way, where is the syntax? Yeah, if you were to do it this way, as I showed you, you get the same information. This is just technically not, I mean, R is not being told that this is repeated measures factor. And so, for this one factor design, it's not a big issue. Once you get into more complicated designs, like a mixed design, then it becomes important to use the real syntax for repeated measures factor.